15 billion trees are lost to deforestation and forest degradation. That's 36 football fields worth of trees a minute, and accelerating. At this rate, the world's rainforests may be completely gone within 100 years. This makes deforestation responsible for around 13% of the world's carbon emissions, making it a major driver of climate change.
Hello everyone, my name is Ahmad Aliff Mohamad, and I am a student from the Bachelor of Surveying, Science and Geomatics Harness program at University Technology Mara, UiTM. So, the title of my research is Comparative Analysis of Deforestation and Tree Cover Loss in Kemasul Recreational Forest by using Random Forest. Today, I want to talk to you about something critical happening in our own backyard. For the past year, I've been conducting a comparative analysis of deforestation and tree cover loss in the Kemasul Recreational Forest using a machine learning model called Smart Random Forest. It's a project that combines environmental conservation with advanced geomatics to see exactly how our forests are changing. Without further ado, let's us dive into the details of the study, starting with the study background and the objectives of the study. To begin, let's look at the context. The state of Ahmad continues to record some of the highest deforestation rates in Peninsula Malaysia. The primary driver is rapid agricultural expansion and large-scale land conversion, which threatens local biodiversity and ecological stability. Specifically, the Kemasul Recreational Forest is a critical habitat and water catchment area facing intense pressure. Currently, there is a significant gap. We lack the real-time insights required to effectively detect illegal clearing over multi-year scales. The research aims to bridge that gap using advanced remote sensing. My research is built on three core objectives. First, map to generate spatial visualizations, specifically land use and land cover, LSC, and NVI maps for Kemasul from 2030 and 2034. 2. Measure to perform quantitative analysis, estimating the exact area of deforestation and tree cover loss using machine learning. 3. Validate to ensure statistical reliability by comparing the accuracy assessment of these findings. To do this, I built what I call a dual-track data pipeline within Google Earth Engine. We pull satellite imagery from SIA for both 2030 and 2034. So we look at the track A, which was the classification side, where we train the Smart Random Forest model to identify different types of land cover. And for the track B, is focus on the health of the forest using NDVI to map canopy density over time. By combining these two tracks, we could verify tree cover loss from two different angles, ensuring our final accuracy assessment was rock solid. The results were eye-opening. If you look at our NVI maps, you can see a systemic decline in vegetation density. In 2030, the dark canopy forest, this decreased healthy carbon sinks were dominant, but by 2034, the map is covered in clearings and low canopy zones. They are just natural change. They are the direct result of human pressure on the forest. Let's start by looking back at our baseline from 2030. At that time, the Kemasul forest was still a massive, uninterrupted dark green center. You can see it here on the map. It's a continuous canopy with only some mirror enrichment happening along the very edge. Now look at the difference in 2034. The change is pretty dramatic. We are seeing massive fragmentation where that deep green core has been rapidly replaced by secondary vegetation and bayland. You will also notice new water runoff zones appearing. It's a classic side effect of large-scale and land clearings that literally change how water moves through the landscape. When we put all the 11 years of data together, our machine learning model gives us a clear look at the degradation zones that are usually missed by manual tracking. The yellow areas you see here represent clearance and low canopy, which basically means total habitat destruction and aggressive agricultural conversion over time. Meanwhile, our untouched canopy forest is visibly shrinking. Now, I wanted to make sure these findings were statistically solid. For both 2030 and 2034, our model achieved an overall accuracy of over 97%, with kappa coefficients higher than 0.96. We essentially eliminate human classification error, giving us near perfect internal consistency for this study. So, what does deal or lead to? What do you think? The numbers tell a stark story between 2030 and 2034. Kemasul lost 4.14 kHz of tree cover due to human pressure. The big takeaway here is that cloud-based machine learning isn't just for academics anymore. It's now a fundamental requirement if we want to manage our forest sustainability and catch illegal erosion before it's too late. Thank you so much for allowing us with this research. Let's keep pushing for better data to protect our planet.